All right, here's the next set of examples. We are still solving the equations. So it's pretty much what we did last time, except for here the book's asking us that we write our answers in exact form, and if the answer is irrational, we approximate it to the nearest thousandth, which is pretty much what we did last time. The first example was irrational. This is not a number we know, and when we put it in the calculator, we saw that it was a long decimal, whereas the second one had an exact answer, not an irrational answer. So for a problem like this, we'd have to write the exact form and then the irrational form, whereas this one we just have one answer. So just like last time, we want to isolate that power, but we notice that on C here, the power is already isolated, so that part's already done for us. So that means we can go straight into the transformation part, where writing a logarithm. Now the base of our power becomes the base of our logarithm, so we have log base 3. The answer to the problem becomes the argument, so log base 3 of 7, and then the exponent becomes the new solution. So for step 8 there, it's actually already done for us once we do that, because there's x solved for, and this would be the exact solution. Now that's not a question we can answer because we don't know what power we need to raise 3 to get 7. So we need to think about how to approximate that. And so in order to do that, how do we figure out what the log base 3 of 7 is? Well, we can't type that in our calculator, but what we can do is change the base. So we're going to use the change of base rule. And what that says is that the log of the argument divided by the log of the base will give us our approximate answer. Or we could, instead of doing log, we could do the natural log of 7 divided by the natural log of 3, and that would give us our approximate answer. So that's what we can type in our calculator. Either one of those two things, it doesn't matter which. So log 7, close those parentheses, divided by log of 3, close those parentheses. And we see that we get an approximate answer of 1.771 when you round that to the thousandth. And if you wanted to check your answer, you could say, is 3 to the 1.771, 7 or something really close to 7. And we see that it is. So our answer makes sense. So here is our approximate answer. So there's the first one. Now the second one, we want to kind of the same way, we want to isolate the power. But what's different about this problem is that there are two powers, and so I can't isolate a power if there's two of them. So essentially what we have to do here is just pick one of them to be our power and the other one to be what the 7 would represent in this problem. It doesn't really matter which one you do. So if you just want to start on with the left, we could think of it that way. And so this is the base of our power. And so remember what the base of our power does, it becomes the base of our exponent, base of our logarithm when we go to logarithm form. So we get log base 4. Now where did the 7 come from? The 7 came from the answer over here. So this 3 to the 2x power is going to become the argument when we put it over here. I'm just going to go ahead and put that in parentheses since it is all grouped together. And then the exponent became the answer when we go to the logarithmic form. So as we write this, it would be equals x minus 1. So there it is. It's definitely strange looking compared to what we've been doing, but that's how you would transform it from exponential form to logarithmic form. And that's, again, just one of the choices. We could have done that with this side and everything kind of switch around, but mathematically it won't make a difference in the end. So what I want to do now is try to solve this, but I have two x's, and that's not good. And one of my x's is up in the exponent, so I need to find a way to get this out of here first. And so what we can do is go to our properties of logarithms and notice that this power here is something I would want to get rid of. So if we use the power rule, we can take that logarithm with an exponent and bring that exponent down to the front of the problem. So this 2x is going to drop in front of my logarithm. So I have 2x times log base 4 of 3, and that's equal to x minus 1. There are many ways to do this problem from here. One thing you might notice is, our x is on either side of the equal sign, so if we actually divide this 2x to this side, that'd be kind of a way of gathering our x's onto one side of the equal sign. So that's gone. Now, as I bring this down, notice I have something where we could basically look at this problem here. We could use the change of base rule to rewrite log base 4 of 3 into a ratio of 2 logs. And maybe once we do that, you might kind of see why we want to do that. So this would be log base, not log base 3, log of 3 divided by log of 4 equals x minus 1 over 2x. And so use the change of base rule to take log base 4 of 3 to turn it into log of 3 divided by log of 4. Remember, both of these are log base 10 now. And this is something we can type into our calculator if we want to. So what can we do with this? Well, look at what we have here. We have a proportion now, and proportions can be solved using cross multiplication. So it doesn't matter where we start, but if I just start here and cross multiply here, we will need to distribute as we do that. Remember, log of 4 is just a number. Almost like, think of this as a 4 or something that we're distributing. So it's 4 times x and 4 times 1. Well, it is a little bit more complicated than a 4, but it's just that idea that it's a number times x and then that same number times negative 1. I'm going to write it a little backwards, maybe what we might think about, but that would be x times log of 4 minus log of 4. So x times log of 4 and then negative 1 times log of 4 gives this. And that's equal to, we do the other cross multiplying. So 2x times log of 3. Okay. What now? So we still have x's on both sides of the equal sign. So that's not awesome. But we can get them onto the same side by subtracting one or the other to the other side. It doesn't really matter which way you go. I'm going to move this log of 4 to the right because I'm going to make it positive. It's the only really advantage to that. And then so as I move this to the right, I'm going to move this to the left. So I'm going to subtract the 2x log of 3 to the side and add the log of 4 to this side. So they're just going to kind of rearrange themselves. So I have x times log of 4, and then that's going to be subtracting 2x times log of 3. And then now that's going to add to both sides, so it would just be positive log of 4. Alright, so we're getting closer. We got the x's on the same side now. What you notice is that both terms here have an x in them. So I can actually just factor that x out. So x times log of 4 minus 2 logs of 3 equals log of 4. And what can get really tricky here is that we just got to remember this is just log of 3 is just a number. I have 2 times x times some number like 5. So if I take the x out, it's just still 2 times 5 or whatever. So this is just 2 times log of 3. Okay, so I have some number minus 2 times some other number. Okay, and then again equals some number. Well, look how close we are to getting x by itself now. So I just need to get rid of this stuff here in the parentheses, and then since it's multiplying the x, we can just divide it away. Okay. So divide by log of 4 minus 2 log of 3 on both sides. So there's what x is equal to. So that's some kind of intense algebra to be doing with the logarithms. The answer certainly looks weird. So there's part A. There's our exact answer. You know, what is that equal to? We're definitely have to type that in the calculator and get that figured out approximately. Pardon? Okay, so we had, let me shrink this down a little bit. Find my calculator now. So log of 4, make sure you close those parentheses, and then divided by, I need to get all of this stuff into the denominator, so I'm going to put parentheses around it, the whole thing, so be careful about that. So log of 4, again, close those parentheses, minus 2 log 3, close parentheses. Now I've opened one set, opened another set, closed one set, open a set, close one set. I still have this first set of parentheses open, so I'm going to close that. So negative 1.709, but the 9 gets rounded up to a 10, so negative 1.71 is our approximate answer. So can we check that? Negative 1.710. Let's go back up to our original problem. So if we plug x into both those things, so what's 4 to the, in parentheses, negative 1.71 minus 1 power? It's this, 0.0233, blah, blah, blah. Okay, well, what about 3 to the parentheses 2 times negative 1.71 power? Better be something really close to that. And we can see that it is. And all the way up to the 10,000th place, they're the same. Okay. So yeah, a lot of intense algebra. Get pretty confusing, you know, kind of keeping track of that idea that a logarithm is just a number. Okay. So we can manipulate it just like we would any number, as far as factoring or cross multiplying and distributing and stuff like that. And so there is that example.